Framework for Assessment of Climate Change-Related Risks to Buildings. Abstract: the paper addresses the increasing risk change in climate poses to building operation and durability. Investors have started to realize that climate change-based risks may affect long-term profitability of their assets. The financial impact of these risks is ambiguous, but various studies have been conducted on how durability of built environment is impacted by change in climatic conditions. A framework has thus been formulated that assesses risks to a region or city through indicators for flooding, rise in temperature, poor air quality, rapid urbanization, and water scarcity derived from literature. The relative importance of each risk has been derived through survey, and the framework has been applied on cities of Chennai, Delhi, and Mumbai. Keywords: climate change, risk assessment, indicators. Background. The causal relationship between human activities and climate change has been well established and acknowledged globally. However, during the last few decades it has been observed that not only the human activities impact climate change, but the change in climate has resulted in severe effect on human activities. This change carries the potential to alter both the man-made and natural systems in all the oceans and all the continents. 1. The reports by the European Commission and the Urban Land Institutes brings forth the impacts the change in climatic factors are likely to have on the built environment in terms of environmental, social, and operational performance and financial implications. The ULI report, on the other hand, divides the risk in terms of the nature of impact, i.e. impacts on the buildings manifest as physical risks, and the other risks of market, regulations, and organization reputation manifest as transition risks. 2-3. Introduction, Impact of Climate Change on Indian Subcontinent. As a background study to understand the variation in climate the Indian subcontinent and Asia is prone to, various literature sources have been studied and the impacts of these changes have been identified. The key risks brought out by IPCC reports include an increase in flooding for riverine, coastal and urban areas which may result in damage to infrastructure along with livelihood and settlements. Another study by 4 focuses on an increased risk of heat-related mortality along with negative impact of heat and humidity on working hours for outdoor activities. 5 emphasizes on increased cooling and heating demands along with an increased risk of inundation, while 6 have also warned against the rise in temperature and increased precipitation along with threat of groundwater depletion. An impending water scarcity has also been brought out in a study undertaken by 7 major cities, including Indian cities, throughout the world. 1, 4, 5, 6, 7. Vulnerability to climatic and non-climatic factors. Globally, urban areas hold approximately half of the world's total population and is formed of most of the built assets and supports majority economic activities. Urban areas are not only at risk due to climate change, but they carry out activities responsible for this change as well. The IPCC report also identifies that apart from climate-based risks, rapid urbanization and growth in these cities has resulted in urban communities becoming highly vulnerable, especially within informal settlements on lands exposed to events of extreme weather. This issue of urbanity sprawling into the erstwhile inhabitable coastal and floodplains is just as much problematic in purview of vulnerability, as is the development of unplanned settlement that replace these land masses. The report describes the decrease in greens, which not only contributes to the urban heat island effect but also decrease the land available for percolation of water, which now gets added to the amount of storm water to be discharged by the already overstressed storm water drainage system 8. This vulnerability of the built environment resulted due to both the climate and non-climate-based factors have been presented through a modified flow diagram of vulnerability presented in the IPCC 2014 report, Figure 1. The paper considers the climatic factors of high temperature, flooding and poor air quality and non-climatic factors of rapid urbanization and water scarcity. Risks pertaining to these factors are studied through the assessment framework. It has been argued that the risk caused by a disaster is a product of the hazard occurring naturally and the number of people and their varying degree of vulnerability. Technically, hazard refers to the natural events that may affect different places singly or in combination at different times. The 3 concepts of risk, hazards and vulnerability thus have been related through the following equation, which has been employed to calculate risk within the study. 9. See research gap. Within the existing indicator-based framework studied, it is observed that there is an absence of methods which are suitable for the varied scales of micro and macro levels of building and cities respectively. 10. Also, a study by 11 states that development plans of cities have failed to explore the ways in which buildings and infrastructure can be adapted to the impacts of climate change. Further, the city-level assessment indicators applicable to buildings and infrastructure studied lacks concerns beyond property inundation, urban heat island effect and occupant comfort. 12, 11, 13, 14, 15. Research aim and objectives. The paper thus aims to prepare an assessment framework for climate change-related risks to built environment. The following research objectives would be undertaken to formulate the framework. I. Identification of various unsafe conditions created by both climatic and non-climatic conditions affecting built environment and their direct impact. 2. Review of indicators for assessment of vulnerability of the durability and operation of buildings to climate-related risk. 3. Preparation of framework for climate change-based risk assessment. 4. Demonstration of framework on case study. 2. Literature review. The literature studied has been divided to address the 5 climatic and non-climatic factors mentioned previously. Research papers on how these factors impact the built environment were searched on Google Scholar with keywords impact of identified factors on building operation, building durability. A list of unsafe conditions and its direct tangible impact on the built environment has been identified and explained in the following paragraphs. About 29 indicators have been explored and derived from these conditions, which have been further shortlisted to 14 on the basis of data available for inclusion within the risk assessment framework. Within the climatic factor of flooding and non-climatic factor of rapid urbanization, unsafe conditions such as loss of green areas and subsequent reduction in percolation of storm water has been identified from a study by 16. Other conditions identified include increase in surface runoff, road length and length of storm water drainage affected, along with risk to properties located in coastal or floodplain. 16. In another research, 17 had identified that increased instances of flooding may particularly damage properties located in areas with soil prone to cracking and subsidence. A study by 18 has further raised the concern of damage to pavement due to improper disposal of storm water or inundation, while the effect of wind-drive rains on building cladding has been stated by 19. Another issue of exposure of larger properties to chlorides due to rise in sea level had been identified in a research by 20 and 21. Unsafe conditions created due to rise in temperature included loss of vegetative heat sink that in turn raises risk of increase in temperature due to urban heat island effect and increased energy consumption due to cooling demand, as stated in papers by 16 and 22 respectively. Further, rise in temperature was also related to fall in efficiency of PV cells, as substantiated by 23. Also study by 24 indicates premature deterioration of outdoor polymer-based materials, while 25 have observed an increase in incidence of electrical fires in older buildings. Factor of poor air quality has been related to acid deposition and the subsequent damage to concrete structure, as per research by 26, along with increasing the likelihood of additional changes in building HVAC system to maintain indoor air quality, as suggested in study by 27. The unsafe conditions created by water scarcity includes, as 7 suggest, increase in reclaiming wastewater and carry out the additional changes to the water treatment infrastructure, and also include water treatment at building level to reduce damage to plumbing system, as observed by 28 in their research. The risks corresponding to these unsafe conditions and the impact of climatic and non-climatic factors on them are further taken up through survey conducted through Google Forms. 23 architects, project managers, and civil engineers with an experience of 3 years and above have been identified for survey, and the results obtained have been analyzed by both SPSS and manual means. 3. Analysis of data. The results of survey have been tested through Cronbach Alpha reliability test, which has been carried out on SPSS of the sample surveyed, and 0.74 score was obtained that renders the survey acceptable. The survey results are further analyzed for identification of relative importance index of these risks. The RII in each case would serve as impact if the hazard for final assessment of risk. The RII has been calculated through manual means using MS Excel and has been added to the final framework for assessment of risk. A. Application of risk framework. The above matrix has been utilized with data particular to Mumbai, Chennai, and Delhi in order to compare their relative risk scores. 2 of the risks of properties in expansive soil and number of electrical fires, with data missing, have been removed. While the 2 risks of flooding of properties within coastal/floodplains and change in vegetative heat sink has been replaced with proxy indicators. Since the values of different risks vary in their scale, the values for each risk have been normalized to score each city in a scale of 0 to 1. For normalization, the technique used in simple additive weighing has been considered given its scaling within 1 and 0. The normalized value for maximum criteria were obtained from n_ij equals r_ij/ r_j max. The normalized value for minimum criteria were obtained from n_ij equals r_j min, / r_j. For a matrix with I equals column number, j equals row number. A multiplication of RII from each of the scores is then summed up to give relative risk scores for each city. As observed from Table 4, Delhi scores the lowest in terms of climate change-based risks, followed closely by Chennai, and Mumbai is exposed to more risk. The assessment undertaken in Table 2 and 3 and the subsequent score in Table 4 is with respect to future climatic conditions have been considered. Future risks pertaining to water stress for the year 2040-34, rise in temperature by 2050-35, increased risk of sea level rise by 2050-36, deterioration of air quality by 2050-37, and UV levels, which has been projected to remain same for 2050-38. Conditions pertaining to remaining risks have been considered based on current values obtained from the sources as per Table 2. A validation of results has been carried out through application of the risk assessment framework on the 3 cities based on current climatic conditions, and the results have been substantiated by the extreme climate-related events experienced within these cities. Based on the current climatic conditions and through normalization of values, the final normalized values and risk scores have been given in Table B. B results. As observed through the risk scores above, Mumbai and Chennai have similar current risk scores. Although Chennai has a higher or similar risk score for the first 5 indicators which have greater weightage in terms of RII, but because of the higher risk Mumbai faces due to lower green cover and higher intensity of wind-driven rain along with greater UV exposure, built environment faces greater risk in the city. Delhi scores considerably lower than the two. This can also be observed from the events of flood in Mumbai in 2017 and 2019 along with Chennai floods in 2015, 2017 and water crisis in 2019. However, the future climate risks as projected in Table 4 show similar climate risks faced by Delhi and Chennai but projects higher risk for Mumbai. For conclusion. Based on the application of framework following it can be concluded that the application heavily relies on availability of data for all the buildings/cities/regions selected. This is important because the risk assessment is not probability-based. It scores the subjects relative to one another. Because of this, the framework can also be applied at various levels with indicators adjusted to suit the scale of the subjects. The risk assessment across the 3 cities can be considered appropriate with respect to the recent events of flooding and water scarcity. But it is also important to note that these indicators identify vulnerability of the built environment and not of human lives. The water stress and flood-related indicators have been given higher RII and consequently Mumbai and Chennai have scored higher. A future scope. The study has been conducted based on existing and proposed indicators that have been derived from the studies on impact of climate change on buildings. However, considering the area of research itself, especially for the Indian subcontinent is at a nascent stage, and owing to the urgency faced by the building sector regarding resilience to climate-related risks, it is important that more studies are conducting establishing relation between climate change and building operation and maintenance. Such studies will help to diversify the indicators used and also help formulate more reliable indicators that can give an accurate description of the risks likely to occur.